One of the most beautiful formulas in mathematics is Euler's formula. It's used a lot in complex variables and differential equations. Let's suppose that z is a complex number of the form a plus bi, where a and b are real numbers. We'd like to try to make sense of what it means to exponentiate z using a base of e. In other words, what is e to the z? So let's substitute a plus bi in. E to the z is e to the a plus bi. Now we would want, however this is defined, we would want the usual rules of exponents to hold. So we would want to be able to break this down into e to the a times e to the bi. That would only make sense. Now let's suppose for a moment that we can do that. We know what e to the a is if a is a real number. That makes perfectly good sense to us. But what is e to the bi where b is a real number? So what we're going to focus on the next few minutes is trying to make sense of how to evaluate or how to define e to the I theta where theta is a real number. We're going to use three important Taylor series that you've seen in calculus to make sense of this. One is the Taylor series for e to the x. It's 1 plus x squared over 2 plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial, and so on and so forth. Now, the cosine has a Taylor series about the origin as well. It has strictly even powers, 1 minus x squared over 2 plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus x to the 8th over 8 factorial. Because the cosine is an even function, this has all the even powers of x, and the signs all alternate. Now the sine of x has a Taylor series about the origin, which, like the cosine, has alternating signs, but it uses odd powers of x. X minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, so on and so forth. So what we're going to do in the next few minutes is we're going to somehow make sense of e to the I theta by using these three Taylor series. So we're going to start by taking the series for e to the x, and we're going to substitute I times theta in. So think about the formula on the previous page. And I'm simply going to replace x with I theta. So I have 1 plus I theta quantity squared over 2 factorial plus I theta quantity to the third over 3 factorial plus I theta quantity to the fourth over 4 factorial plus I theta to the fifth over 5 factorial, and so on and so forth. Now, this is the same as I squared theta squared over 2 factorial. This is the same as I to the third theta to the third over 3 factorial. This is the same as I to the fourth theta to the fourth over 4 factorial. This is the same as I to the fifth theta to the fifth over 5 factorial, so on and so forth. Now we're going to make use of the fact that the powers of I simplify. In particular, I squared is negative 1, so we could replace this with a negative 1. I to the third is minus I, so we can replace that with minus I. I to the fourth is 1, so we can replace that with 1. I to the fifth is I, and so on and so forth. So when the dust settles, the terms that don't involve I will be this 1, this term, and the next term would be theta to the 6th over 6 factorial. So we're going to take this infinite series and we're going to put all the terms that are real numbers together and those that involve I or are complex together. And so let's take a look at the terms that don't involve I. We're going to have 1 plus theta squared over 2 factorial, but this is negative 1, so we'll have minus theta squared over 2 factorial. Because this is 1, I'll have theta to the fourth over 4 factorial, and so on and so forth. Now let's take a look at the terms that do involve I. This will be I times theta. This is the same as minus I, so I'll have minus I theta to the third over 3 factorial. This is the same as I times theta to the fifth over 5 factorial. So I can factor an I out of each of those terms, and I'll have theta minus theta to the third over 3 factorial plus theta to the fifth over 5 factorial. So again, when we simplify this term, that term, that term, they will not involve I. But this term, and this term will involve I. And so we're grouping together those terms that don't involve I and those terms that do involve I. But this is just the Taylor series for the cosine. So this is the cosine of theta. And this is the Taylor series for the sine of theta. So what we have in the end is that e to the I theta simplifies to be just cosine theta plus I sine theta. And that's what Euler's formula says. So there it is in all its splendid glory. E to the I theta is cosine theta plus I sine theta when theta is a real number. Get focus there. Let's take a look at some examples. E to the 2 pi I. By Euler's formula, our value of theta is 2 pi, so this would be cosine of 2 pi plus I sine of 2 pi. We know the sine of 2 pi is 0, the cosine of 2 pi is 1, so e to the 2 pi I is 1. E to the I pi over 2, in this case theta is pi over 2. So we have e to the I pi over 2 is cosine pi over 2 plus I sine pi over 2. The sine of pi over 2 is 1. The cosine of pi over 2 is 0, so we just get I. What about e to the I pi over 3? In this case, theta is pi over 3. So we'd have the cosine of pi over 3. That's a 3 there. I'm going to see if I can focus this again. Plus I times the sine of pi over 3. Now the cosine of pi over 3 is a half. The sine of pi over 3 is root 3 over 2, so I'm left with 1/2 plus I times root 3 over 2. Let's take a look at e to the I pi plus 1. Let's simplify this expression. This would be by Euler's formula. We'd have cosine pi plus I times the sine of pi. That's this part. And let's add that 1 on. The cosine of pi is -1. So that's going to cancel with this one. And the sine of pi is equal to 0. So what I'm left with is this amazing formula, e to the I pi plus 1 equals 0. It's a formula that combines 5 very important quantities: 0, 1, pi, I, and e. That's amazing. How amazing is it? Well, one of my former students thought it would be really cool to get a tattoo of that equation on his arm. So this is what it looks like. Here are some problems that I'd like for you to do in preparation for class. I would like for you to evaluate exact values for each of the following: e to the 2 pi I over 3, e to the 4 pi I over 3, e to the minus 5 pi I over 6, e to the minus pi over 2, that's an I, and e to the 10 pi I over 3. So evaluate each of these exactly. You'll need to recall some basic facts about the unit circle.